So yes, I'm Samuel Ortiz. I work for Apple, and today, yes, I'm going to talk about confidential containers. I'm really happy that Moritz presented and gave a very nice presentation, short one, but very nice presentation about Kubernetes, because I didn't have that. So thanks a lot for this. And yeah, confidential containers. This is a project that we started about a year ago, and really the idea is to make confidential computing a commodity for Kubernetes workloads. So let's look at the goals of the project. What is it? What is it really trying to do? And the next section of this presentation will look at how we're trying to do this and what are we going to do next and what have we delivered so far. So first of all, two very high-level major goals. The first one, I think, is common to a lot of confidential containers projects, which is basically removing the infrastructure from the TCP. I think here we're talking about the cloud-native infrastructure. The second one is very specific to confidential containers. We're really trying to standardize confidential computing at the pod layer, and I insist on the pod layer part. As Moritz explained in the previous presentation, what we're trying to do essentially is to give each Kubernetes pod its own confidential computing enclave. And I'm going to go into more details in the next slides. But first, a set of attributes of the confidential containers project. The very first one is transparency and seamless. We really want to run those Kubernetes workloads unmodified. We are not asking for any container images changes, no pod configuration changes, no hardware implementation specific bits and pieces. It's all completely unmodified and completely seamless and transparently integrated into confidential containers. And without those restriction of having to be very specific about confidential containers, we still are giving one confidential computing enclave per pod. Confidential containers as a project is hardware agnostic, TE agnostic. So we want to support as many TEs as possible. And I'll talk in more detail about which ones we support, which ones we try to support. And we are providing a hardware independent API or user experience. The user and the DevOps engineer that doesn't have to know about TEs, doesn't have to know about which TE implementation it's going to be running underneath. It just has to enable confidential containers and things should work transparently. And last but not least, this is an open project, open as in it uses only open source components and nothing else. The community around it is open, so we have weekly open meetings where we discuss the project, and the governance around the project is also open. It's currently being defined, but the idea is really to make it completely transparent and open. Okay, so let's look a little bit deeper. Let's go into more details about the architecture of the project and how we are implementing this. And again, as the goal is to provide a confidential computing enclave to each and every Kubernetes pod running on a cluster. We want those pods to run in their own exclusive TE-backed enclave. Inside that enclave, we have a minimal software stack that's running, and that is measured and attested. And this is the only part that's measured and attested. The container images that make the Kubernetes pod are not measured, they're not attested. What we request from the guest owner is for those images to be encrypted or signed, or a mix of those two. And really, the enclave stack, the minimal enclave stack that's going to be measured and attested, is going to be responsible for pulling, decrypting, and storing those container images. So that's the high-level architecture. If we look at the flow to understand a bit further on how this is all working, let's look at how we would start a confidential container, which is a confidential pod inside a Kubernetes cluster. So the first thing we do is to create an enclave a TE-backed enclave for each pod that's running on the cluster. And this pod, this enclave, sorry, is going to run a minimal and measured software stack. This software stack contains a few things, but it at least needs to contain an enclave agent. And I really want to highlight this part because this is very important. This software stack, the software stack that boots the enclave, that starts and the enclave from scratch, does not contain any container image. It doesn't have and carry any container image. And last but not least, a very important point, the same software stack is going to be reused across all pods. So you don't have to create a custom software enclave stack for your specific pod containing the images. It's all going to be the same software stack and we'll see that in detail right away. It's all going to be the same software stack that pulls the container images. So we have this enclave assigned to our pod that it's backed by a TE, and it booted this minimal measured software stack. The very next thing the enclave is going to do through the enclave agent, which is part of the measured and verified stack, is to fetch the container image keys. Again, we are requesting container images to be encrypted or signed or a mix of the two. And the enclave agent, the first thing is going to do is to fetch the container image keys, and it's going to get those from a relying party running a key brokering service. So that relying party is owned by the guest owner and controlled by the guest owner, and it's going to provision the software enclave stack with the container image keys. And to be provisioned, the software stack needs to be tested and verified. So as it's measured, the minimal enclave stack is the one that's being attested. And once it's attested and verified, the relying party provisions this stack back with container image keys and cryptographic materials. And again, container images, they're not part of the measurement. They're not verified, they're not attested. Once the enclave agent get the container image keys back from the key brokering service after attestation was successful, hopefully, what it's going to do is going to pull the container images. Those container images, again, are encrypted. So it's going to use the provision keys to decrypt the container images and unpack those container images inside the enclave. So the container images, as opposed to the current Kubernetes architecture, they're staying inside the pod. They're not owned and managed by the host. And I'll talk a little bit more about this in the next slide. So the images are kept inside the enclave, and once the enclave agent has been able to pull, decrypt, and unpack those images, it can now start and manage the Kubernetes pod itself because it has all the data that it needs to do so. So if we look at it in more illustrative way, and this is the generic architecture, I'll go into more details on how we actually implemented this with Kata containers. So we have a Kubernetes node with confidential computing hardware. First thing we are going to do, and we as in the runtime that's managing the Kubernetes pods, is going to start and create a Kubernetes pod enclave. And actually it's going to start by booting the software stack, the enclave software stack that at minimal contains an enclave agent. This part is, again, the part that's measured across the entire stack. The software stack is booting, and on outside of the cluster, we have a relying party running attestation service and key brokering service. And the enclave agent, first thing it's going to do is going to ask for keys in order to pull, decrypt, and unpack container images. And this is going to be done by reaching out to the attestation service, actually requesting for a key, and the attestation service, the key brokering service, is going to reply with a attestation request. And the enclave agent is responsible for running the entire attestation process. And if that is successful, then the key broking service provisions the software stack, the enclave software stack, with the container image keys. At that point, we just have an enclave software stack, a minimal one, that's managed to attest itself and verified, and is verified, and get container images keys back into the enclave. Now that it has those keys, it can start and pull the container images from any registry, trusted or untrusted. Again, the container images are going to be encrypted. So this is something, it doesn't matter where those container images are living. They're going to be encrypted or signed, depending on how you want to protect your data. So the agent pulls the images, and given that it has now the container image encryption keys, it can decrypt those keys inside the pod enclave. It decrypts it, unpack them, and again, those images, those container images, the data that makes the actual pod workload is in the pod enclave. It's part of the trust domain. So now that it's decrypted, verified, and unpacked, the agent can start running the actual pod by launching the container based on those container images that, again, are living inside the Kubernetes pod enclave. So that is the general architecture. This is how we want to do it, how we actually wanted to do it. Now let's look at a little bit, again, more in details on how we actually implemented this through our first version of computational containers. So we use Kata containers, and computational containers v0 is based off Kata containers. In terms of TEs that we support with computational containers v0, we support SEV, TDX, and IBM's secure execution. The pod enclave, in my example, the Kubernetes pod enclave is a virtual machine. Those technologies here, SEV, TDX, and SE, are virtual machine-based computational computing implementations. The enclave stack, the minimal stack that I've been talking about that is measured, is basically the Kata containers Linux guest. Again, it doesn't contain the container images. It typically will contain potentially a firmware, a Linux kernel, a kernel command line, and an initronfs or some rootfs image, but no container image. The enclave agent, the agent that's running inside the enclave stack, is the Kata container agent. But compared to the vanilla Kata container agent, it's enhanced with image management features and capabilities. And it actually talks to another piece of software that I'm going to talk about, which is the attestation agent. So again, to be more illustrative, this is the actual implementation of computational containers version 0, our first release computational containers. In the left side, in the left hand side, you see the Kubernetes control plane, where the Kata runtime will use KVM and any VMM, QEMU, cloud provider, or some others that supports computational computing to launch a virtual machine and boot the minimal Linux guest. And that is the software enclave stack that I've been talking about. This part is measured again. And this part will run the Kata agent. And the Kata agent is the main software component that runs inside this guest. And in order to run the attestation process and get provisioned back with the container images keys, it calls into the attestation agent, which is another piece of software, another software component that we implemented in computational containers. If you compare this architecture, this computational containers v0 with what we currently do with Kata containers, there are two major differences. The first one is that with regular Kata containers, which allows us to run Kubernetes pod inside regular virtual machines, not computational computing virtual machines. With regular, with the upstream vanilla Kata containers, we don't have any attestation process. So the agent, obviously, it's not measured. It's not going to be verifying the guest software stack, and it's not going to be talking to a relying party for getting keys provisioned. The other major difference is how image management is done with Kata containers, and actually it's more than with Kata containers. It's actually a generic Kubernetes assumption that images, container images, are going to be owned by the by the host. So the host is going to be pulling the images, is going to be unpacking the images on the host file system, and is going to be typically mounting those container images for the pod to actually consume them. So having the host being able to pull, unpack, mount, and potentially decrypt container images is really breaking the confidential computing model that we're trying to build with confidential containers. So we are switching this assumption and making image management stay inside the guest. So we call that container image offloading, and this is just what I talked about, where the host with confidential containers and how we offloaded container image management, the host no longer manages container images, and this is again a big difference and a big change of assumption compared to what Kubernetes expects. So the host no longer pulls or mounts container images in the host file system, and to do that, we actually worked on Containerd, which is a container runtime that is deployed in Kubernetes deployment. So we work on Containerd so that it now offloads the image service to Kata containers. Kata containers itself offloads this service to the guest, and the guest is going to be responsible for completely controlling the image management. And the image management layers are now embedded into the Kata agent, which is again the enclave agent that I've been talking about. And Kata containers carries a new container image RAS crate called image RS, and image RS will call into a new crate that we work on, OCI crypt RS, to decrypt the encrypted container images. And OCI crypt by itself cannot decrypt; it needs the keys for these container images. And so OCI crypt uses the attestation agent to actually get the keys back from the key brokering service. And the attestation agent is the other software component that we worked on, actually one of the many software components that we worked on as part of the confidential containers project. And really its high level role is to request encryption keys for the agent, the Kata agent, the enclave agent, to decrypt those container images. But to do that, it talks to a key brokering service, hoping that this service is going to reply back and provision the enclave stack with encryption keys. But that only happens after attestation is successful. So the attestation agent is not only responsible for requesting the keys, but it's also responsible for replying to the attestation request that the key brokering service and the relying party is going to initiate in order to provision the keys. The attestation agent is following a very modular architecture. So we are supporting a different key brokering service, and we are really designing the agent so that we can add more key brokering service implementation to the code base. And also on the client side and how attestation and measurement is built, the attestation agent, again, as the goal of being very modular and is willing to support multiple TEs. And yes, the TEs that the attestation agent support today are all those 3 TEs that I've been talking about, which is TDX, SEV, and IBM's Security Execution SE. So that's all nice, and it actually works pretty nicely. You can, with confidential containers v0, you can start a Kubernetes pod in your public cloud, and as long as it provides access to confidential computing, one of the TEs that we support, you'll be able to run a pod exactly the way I just described, where the agent is measured, the whole Linux guest is measured, and will pull the container image inside the enclave. But we do have some gaps, and I'm gonna talk about this now. One of the biggest gap that we have is that we don't support storage and volumes. And Maurice in the previous talks highlighted the fact that this is a key part of any Kubernetes deployment. So we need to address that gap. The other gap is that we don't support process-based isolation TEs, like, for example, SGX. And last but not least, I think one of the, it's not a gap because we are running tests and we have ways of deploying computational continuous v0, but we need to improve on this. So first of all, storage and volume. As I said, volumes is really a key Kubernetes features, but with computational continuous v0, there was no way of basically sharing a volume provided by the host back into the guest. So how do we share data provided by the host in a safe, secure, and I would say computational computing compliant way? The way we're going to do this with computational containers v1, because I'm going to now start talking about computational container v1, because this is the next version of computational containers, and this is the one that's going to address those gaps that I just highlighted. And the way we're going to do this with computational containers v1 is that we are going to request volumes provided by the host to be encrypted, and they will be decrypted from the enclave with either the key that's been provisioned at the very first request by the attestation agent, or by any further request that the attestation agent would do in order to decrypt one or many volumes. Initially, we're only going to be supporting block or network-based volumes. And as I said, the guest owner is going to be requested to encrypt those volumes and provision the cluster with encrypted volumes that we will be decrypting. Computational containers will be decrypting from inside the enclave. So with that approach, the host no longer owns and mounts volumes. Today, Kubernetes for sharing volumes with, for example, Kata containers will mount volumes on the host and use technologies like VirtIFS in order to share those volumes inside the guest. With the computational containers v1, we no longer can do that because the host can no longer mount a volume that it cannot decrypt. So we're breaking that assumption. We don't want the host to be able to own and mount the volumes, and we want those volumes to be encrypted. So if we look at what we're going to do, the volumes are going to leave on the host, but they're going to be encrypted. We're going to share those volumes through technology like VirtIO block, and we're going to decrypt those volumes inside the Kubernetes pod, living in the enclave by using the provision encryption keys that we get from the key brokering service. Another thing that I didn't mention in the previous slide is that we also want to support as an option ephemeral volumes, where the guest owner would be able to provide an empty or dummy volume for, how would I say, optimizing how container images are going to be stored inside the pod enclave. With computational containers v0, the images are kept inside the enclave. And as a matter of fact, they are using a very precious resource, which is encrypted memory. What we want to do with computational containers v1 is allow the guest owner to provide a volume that's going to be shared inside the guest. And the first thing the guest is going to do is going to be wiping this volume entirely and encrypting it with a provision key that the host has no way to know about. It's going to encrypt this ephemeral volume and then be able to no longer store the container images inside the encrypted memory, but use that volume to store it in a safe and non-host visible way. Okay. Next gap we want to address is process-based isolation TEs, also known as SGX. How can we support SGX? We want to support SGX, but we want to keep following the same architecture principle that I described, which is use the TE to create a Kubernetes pod enclave and pull the image from that enclave and pull the images from that enclave and run the pod from that enclave. So this is currently being discussed in our GitHub repos, and this is a proposal that we are currently looking at. And the way we are thinking of doing this is first start what we call a stub SGX enclave, and there's going to be one stub SGX enclave per pod. And the single role of that enclave, that stub SGX enclave, is to act as a container image management proxy. So the only thing it's going to do is going to be pulling the container images and storing those container images on the host in an encrypted file system. Then for each application composing the Kubernetes pod, we're going to start a new enclave. So it's going to be one enclave per container composing the pod. And this enclave is going to use the images that the stub enclave has fetched and stored and encrypted on the host file system. In order for the application enclave to use those container images, it needs to get the keys that the stub enclaves fetched and was provisioned with by the key brokering service. And for that, we want the application enclaves, and again, there's one of them per container, to run local attestation with the stub enclaves and get the keys provisioned from the stub enclave into the application enclave. So if we look at it, we're going to have the stub enclave here. That's going to be started by as an SGX enclave, and very similar to what we're doing with TDX and SCV and SE. The stub enclave is going to run a minimal software stack, and is going to be running remote attestation against an attestation service. And if that is successful, it will be provisioned with container image encryption keys from the key brokering service from that relying party. When that is done, the stub enclave is going to be able to store store the container images in the encrypted file system that it then will be able to share with the Kubernetes pod. And the Kubernetes pod in that architecture is going to be made of a few SGX enclave, application enclaves, where for each container we're going to have one SGX enclave that's going to run local attestation against the stub enclave, and will be provisioned with the keys that the stub enclaves has been provisioned with initially, in order for those application enclaves to use, well, decrypt and use the encrypted file system that's now living in the host file system. Okay, the last major part of confidential containers V1 is CI/CD and deployment. Well, CI/CD first. So we want to integrate with the Kata containers main branch. We want to be the Kata container CI is very extensive, runs a lot of Kubernetes tests, and our goal is really to merge the current confidential containers branch into the main branch so that we can leverage this pretty big CI machine and run regular Kubernetes tests with regular workloads on top of confidential computing hardware. Talking about hardware, we're having silicon vendors like Intel, IBM, and AMD that are adding confidential container hardware to the Kata container CI so that we can run those tests not only against regular machines, regular cluster, but also against machine and nodes that would be running confidential computing hardware. And we're also going to add some confidential computing specific integration tests against different Kubernetes, different key brokering services, for example, that won't be part of the main Kata containers CI. The last thing we're working on with confidential containers V1 is the Kubernetes operator. For those who are not familiar with what a Kubernetes operator, it is what it tries to replace a human operator in terms of how a Kubernetes cluster is provisioned and deployed. And we are building this with confidential container V1 in order to build and deploy all the confidential containers artifacts in a very easy and automated way in an existing Kubernetes cluster. There are many of them, confidential containers artifacts. The guest image is special. The guest image, as in the software enclave stack that I've been talking about. There are some configuration files that needs to be provisioned as well, and a few other things that this operator will provision in the Kubernetes cluster and allow actual users of the cluster to then be able to launch Kubernetes confidential pod in a completely transparent way. With that operator, we will have a native integration with Kubernetes. Okay, so what is the status of the project and what is our roadmap? I've been talking about V0 and V1. V0 was released on December 2021 with very active contributions from a few key stakeholders, IBM, Alibaba, Red Hat, Intel, AMD, Apple as well, have been contributing to the project. And we're looking at CCV1 to be released by May 2022. And again, CCV1 hopefully will fill all those gaps that I've been talking about. And last but not least, links. If you want to go even deeper, if you want to start looking at the code, if you want to try to deploy this by yourself, if you want to look at demos, so we recorded a few demos of confidential containers on top of all the TEs that we currently support. So we have demos for V0 on top of TDX, SCV, SE. We have a demo of Kubernetes operator. This is all on YouTube, so it's something that everyone can watch and enjoy. And if you want to join the project, if you want to or even listen to what's happening, we have a weekly meeting every Thursday, and everyone is very welcome to join and contribute, participate to this project.